Well, hello there. So let's talk about serial communication. There are several different kinds, and we'll go over the different types and what exactly they mean. I will point out there's a very nice video here. I'll put the link on our class webpage too. This goes through the same types of serial communication with some nice examples using oscilloscopes, better visual aids than you're going to see here. So the goal for all of these serial communication schemes we're going to talk about is to send a number, an 8-bit number. So we have to send 8 bits somehow from one device to another. So we have a number like 37. We want to send that. So that's stored in binary. Here's the binary representation of 37. Then we have some communication scheme, serial, parallel, whatever, certain kinds of serial. That's what we're going to talk about today. And then it gets received as a binary number, either bit by bit or as the whole thing, and we convert it back to a number. So all of these just send a number, and they all default to an 8-bit number at a time. So if you have a 16-bit number, you break it into two 8-bit numbers and send it that way. So binary, because we're using electrical signals on-off, really defaults to binary. Binary takes a lot of space. In order to type a binary number, you have to put all of those bits in. Hexadecimal is base 16. So the digits go 0, 1, 2, 3 through 9, and then A is 10, 11, 12, 13, 14, 15. So base 16 needs characters for 0 through 15, just like base 10 has numbers for 0 through 9. And every 4 binary bits is easy to convert to one hexadecimal digit. So rather than an 8-bit binary number, you can write it as a 2-hex digit hexadecimal number. And so because it converts directly, every 4 becomes a character, and the next 4 become a character. It's a shortcut way to write binary. And so this is what programs like C use by default. And 0x in C is the way to tell the C compiler that you're writing a hexadecimal number and not a decimal number. So 0x03 could be base 10 or could be base 16, but here the 0x means it's base 16. You can also use decimal when you're using C. It will convert for you. But hex, because it maps directly to every 4 bits, is the most common way to do it. If you're trying to send characters, the most simple way is to use a table and assign each number to a character. So the ASCII chart is the one that's been around forever. And this is a table of the ASCII chart, and you can see that the letters start over here. This is the decimal representation, binary, octal, which is base 8, which is not very often used. Hexadecimal is here, and then ASCII. So capital A is 65. So you can send numbers. This is how your serial port works when you do print, serial.print in the Arduino. It converts your letters into numbers and sends the numbers, and then the serial terminal on your computer converts the numbers back into characters using this lookup table. Just to zoom in a little more, we can see the capital letters start with 65 and they go in alphabetical order. Lowercase starts with 97 and goes up, and there are quite a few non-printable and control characters and things too, especially in the lower numbers. So we're going to talk about serial communication today, but to start with we can talk about parallel communication because it's actually easier, because if you want to send an 8-bit number, you can use 8 wires. So parallel means you use 8 pins to send all 8 bits. And if you look at the chip that's on our Arduino, the Uno and the Nano, the pins are actually grouped into sets of 8. So port D 0, 1, 2, 3, 4, 5, 6, 7. So there are 8 pins, and they're grouped as one port. So you can set port D to a number, and that will send values to all of these pins at the same time. The Arduino breaks them out into individual digital pins, but inside the chip you can set 8 at a time. So if we're doing parallel with fingers, this is something that's more fun to do in a classroom where we can hold up our hands and communicate with each other. But to use fingers, you would need to use 8 fingers at a time. You would assign each finger to be a bit, and then whether you hold it up or retract it is on, a 1, or off, a 0. So this is a 1 for all the bits, 0, 1, 2, 3, 4, 5, 6, and 7 is a 0. Remember, bit 0 is always the least significant bit, the bit on the right. So this is the first bit, bit 0. The second bit is bit 1, and we go all the way up to bit 6 and bit 7 there. So get used to the numbering. It starts with 0, ends with 7. So now that we understand parallel, what serial does is it uses fewer wires. You need 8 wires to send an 8-bit number over a parallel port, and that's inconvenient for wiring. So serial sends 1 bit at a time, one after another. Serial means one after another. And so we're going to talk about 3 different kinds of serial communication. The first one is called asynchronous serial. It's also what an RS-232 serial port uses, which are in old computers, have serial ports like this. UART is another abbreviation for that. Universal Asynchronous Receiver Transmitter is what UART stands for. So sometimes just serial port, sometimes they call it a UART. RS-232 and RS-485 are using asynchronous serial with specific voltages. So a lot of names. This has been around a long time. So our Arduino has a single UART serial port, and it's the one that we use for serial print and also programming. It's connected to the USB to serial converter on our Arduino boards. The serial terminal sends text using the ASCII table. So 65 means A, 97 means lowercase a, and so forth. Other sensors use asynchronous serial. GPS is the NMEA standard is a serial standard, and there are lots of other devices that use serial communication. It's a simple enough protocol. You can actually just do it by turning the pins on and off yourself in software. So if you need more serial ports, this is one approach. It's called bit banging in the hobby area, because you bang out each bit in your 8-bit number by hand here. The built-in serial port, you can just send it a number and it will handle it in the background for you, and it will also receive in the background and store the data until you're ready to read it. So in terms of wiring, you really need just 2 wires to do asynchronous serial, and sometimes you only use one or the other, depending if you're communicating back and forth or just in one direction. So TX stands for transmit, and RX stands for receive, and the wiring here is a little confusing to people sometimes. You have to connect my transmit connects to your receive. So you don't connect TX to TX and RX to RX if you're trying to connect your GPS to your Arduino. TX connects to RX and RX connects to TX. So you're listening on RX, they're transmitting on TX, you're talking on TX, and they're listening on RX. So make sure you connect these the right way, or else it won't work at all. There are other pins. If you look at a standard serial port on a PC, there are flow control pins to say, I'm not ready, wait, 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 kind of things. But those are optional and not usually used these days. Now we send each bit over the wires, and so we have to hold it for a certain amount of time. And for asynchronous serial, the data, each bit is timed by agreeing on a baud rate. Baud means bits per second. So 9600 baud, you've probably set your Arduino to communicate at that baud rate. That means 9600 bits per second being sent out. So 1 bit is 1 over 9600 seconds long. The other thing you have to agree on is what voltage levels to use. So RS-232 is an old school serial communication, and a 1 in RS-232 is a negative voltage. -3 to -15 volts is the official 1, and 0 is in the range of 3 to 15. So people call it inverted because 1 is low voltage and 0 is high voltage. And the original specification says that 0 volts is neither, and that's kind of an error checking. If you're getting 0 volts, you might have been short-circuited to ground somehow. So this lets you reject those and show up faults in the system. Often, though, in modern RS-232, 0 volts works instead of a negative voltage, just because it's easier to build them that way. TTL is transistor-transistor logic. This is the one that the Arduino uses. And a 1 is 5 volts if it's a 5-volt chip, or 3.3 volts for something like the ESP32 chip. And 0 is 0 volts. So this is the more common one you'll see these days. So on an oscilloscope, this is what you're going to see. To send 8 bits of data, we also have a start bit before and a stop bit after. So to send 8 bits, you have to actually send 10 bits. And the way it works is when we're not sending anything, we leave the line at the high voltage, the 1 voltage, 5 volts on your Arduino, and then you're listening, and when you see that wire, that this is the transmit on your Arduino, TX drops to 0 volts, we know that there's a transmission coming. So the start bit changes the state here, and you start your stopwatch on this falling edge, because you know if it's 9600 baud that in 1/9600th of a second after this, the first bit data is going to come in. So whether it's a 1 or a 0, you'll either get 5 volts or 0 volts, and then one more bit time you'll get the next bit and the next bit and the next bit, and they just get sent according to the baud rate. Most modern UARTs will actually sample like 3 times, and then they vote for which one in order to reject noise. If you're doing this yourself or looking at an oscilloscope, you would just look at the data here. So you send this, you go from high to low, that's the start bit, then you send bit 0, either a 1 or a 0, then bit 1, a 1 or a 0. So here's bit 0, so we get 5 volts, then 0 volts, then 5 volts, 5 volts, 0 volts, then 5 volts, and so forth until we get to bit 7, which would be a 0 here, and then we go back high. 5 volts again is the stop bit for 1 bit period, and that just lets everything settle out, and it keeps us high. And then when we go from high back to low, we know we're starting a new set of data. And then if we're done, we leave this thing at 5 volts so that we know it's not being used. So if we were going to do this with our fingers, you only need 1 finger to transmit serial data. Asynchronous serial just uses 1 wire, which is why it's convenient, and you need a ground, of course. But if I'm going to do it with a finger, I have to do it very slowly because I can't think that fast. So I will change up or down every 2 seconds. So 1 1000, 2 1000, 1 1000, 2 1000. And I would read this off. I would start with a 1. Then I would go down for the start bit for 2 seconds. Then in that next 2 seconds, I have to set either the 1 or a 0 for bit 0, and then the 1 or a 0 for bit 1, and then the 1 or a 0 for bit 2, and then a 1 or a 0 for bit 3, bit 4, bit 5, bit 6, bit 7, and then I go high, 5 volts for the stop bit, and I'm done. The timing doesn't need to be very precise in terms of what you're timing hardware. You can have a very cheap stopwatch because we're only timing from the start bit to the stop bit each time. So if you have a little bit of error that builds up, it doesn't take very long and you won't build up much error. That's one of the ways that this is a robust system. So take a look at this drawing. Here's a quiz. We're trying to find out what's the baud rate of this transmission what number was transmitted. This is a graph on our oscilloscope, and we're using RS-232, and so we're trying to transmit. So here high voltage is a 0 and low voltage is the 1. So remember that for RS-232 versus TTL. We want to know what's the baud rate, what number, and what letters that correspond to. So here's the timing down here in milliseconds. And here's the data coming in, and it's actually labeled start, stop, and bits. There's an optional parity bit here that we can ignore for now. It's an error checking. It does some math on these and then puts the answer as the parity bit, but it's not usually used. It just was in the picture that I had. So take a minute, pause the video, try to answer these 3 questions. Okay, so here's the answers that I got. So the baud rate, we just look at the timing. So for 1 bit, how much time between here and here. So on this scale, we've labeled every other bit. So we get 2 bits, the start bit and bit 0 in 0.4167 milliseconds. So we want it in bits per second. So 2 divided by 0.4167 times 10 to the minus 3 in bits per second is 4800 baud. This is a very slow data rate, commonly used by the NMEA standard. The number that was transmitted, it's tempting to just read them off here. So if we have a high voltage, plus 12 is a 0, minus 12 is a 1 here because we're using RS-232. This was TTL. Up would be 1 and down would be 0, but in this case it's that backwards thing because of historical reasons, I guess. This is the rightmost bit, the least significant bit. So we get a 0, 1, 0, 1, going backwards, 0, 1, 0, 1. Then we get 0, 0, 1, 0, 0, 0, 1, 0. So if you write them out in the order that they come out, you get this binary number, 0, 1, 0, 0, 1, 0, 1, 0, because we start from bit 0 and go to bit 7. That's the binary representation. That's 112 in decimal, or 4A in hexadecimal. And according to the ASCII table here, that's capital J. So that's asynchronous serial, or a UART. The next communication standard is SPI. It stands for Serial Peripheral Interface. That's actually trademarked, and so the generic term is a 3-wire interface. And this is the next simplest one. And the big change here is that it uses a separate wire to time the data. So it's clocked. So asynchronous means there's nothing synchronizing it because we use a stopwatch. Here we're synchronous serial because we have a clock line that's just toggling. This square wave is the clock, and that tells us when to go from bit 0 to bit 1 and so forth on the data lines. The lines are, you need 4 wires, even though it's called 3-wire protocol. You need 4 wires. You have the clock line. Now here, the terminology is very old-fashioned, and there's a big push to get rid of the master-slave terminology, and I think that's a really good thing to do. And so you'll see other things. I don't think there's a real well-established standard, though. People are trying to find things that use M and S so that they don't have to change the acronyms. Other people are just trying to change, to controller and peripheral, things like that are other ways to go. So hopefully we'll have a standard pretty soon, but these slavery references really are not the way to go. So having said that, MISO is master in, slave out. There's one device that's controlling, driving the clock, and the other one is listening to the clock. That's the difference here. So the master is running the clock, the slave is reading the clock but not driving it themselves. So master in, slave out, this is the peripheral talking to the controller. Master out, slave in, this is the controller talking to the peripheral. So data flows in both directions at the same time, always. Sometimes you just ignore one. If you're only sending data, you don't pay any attention to what's being received. But the standard is that data flows in both directions at the same time. And there's this SS pin is for slave select. And that's so that you can have multiple devices using these wires and only talk to one at a time using this wire. So when the slave select wire goes from high to low, that means I'm talking to you, the peripheral, and then the master, the controller, starts clocking the clock line in this nice square wave, and then the data flows on the data lines. So you can, if you wire these together, MISO goes to MISO, and MOSI goes to MOSI, and S clock goes to S clock. So it's not like RX to TX in the other serial, in the asynchronous serial. So you wire the same names together. And there are a lot of variations on this, whether you use the rising edge or the falling edge here to send the data or set up the data or read the data. So it's not very standardized and you have to read the data sheet. So this is just one example. So if we think about how this would work with fingers, you need a few different fingers to send this. The slave select is when I'm pointing to you. You listen now, and everybody else is connected and can see the data but is ignoring the data. That's the SS. So when the SS goes low, the peripheral device is going to pay attention to this. And then we need a clock line. So when we do this in the classroom, I flip the lights on and off because it's easy to see. So imagine this is the light switch turning on and off. Lights on, lights off, light, dark, light, dark. That's the S clock line. And then we have two data lines. MISO is the controller receiving data, so I listen to this, and you set data on this. And then this is where I'm sending data. The controller sends data, master out, slave in. This is me sending data and you listening to the data. And you can see these rising and falling edges come in different parts of the data line. So the red is the rising edge, the light's going on. That's when we read the data. We're right in the middle here. It should be nice and stable. And on the falling edge, when the lights go from on to off, I know that's time to set my next data point. So the slave select comes down, and I set up my first bit. Then when the clock goes high, from low to high, so lights go on, I'm going to read the bit, and you're going to read the bit. Then the lights go off. You're going to set up your second bit, and I'm going to set up my second bit. That's when the lights go off, we set them up. Then when the lights come on, we each read the bit. Lights go off, set up the next bit. Lights come on, read the next bit. Lights go off, set up the next bit. Lights go on, read the next bit, and so forth. So we're using this to know when to set up data and when to read the data. We don't have to agree on the timing ahead of time, so it's flexible that way. And if I get stuck, if things are going badly for me, I can just stop toggling this, and everybody should wait until they start toggling again. So usually it's done at a standard rate, a steady pace here, but it's possible to stop and handle things that are coming up. So that's a synchronous serial communication called SPI, or three-wire. The most common thing you'll see these days is SD cards. One of the ways, there are different ways to talk to SD cards, but one of them is using SPI. So you can buy these little boards that would connect to your Arduino. There's a data in, data out, and clock line, and the chip select. So that's SS, MOSI, MISO, and S clock on these wires here. SD cards by default are 3.3 volts, so if you drive them from your Arduino Uno, that's 5 volts. You'll burn your SD card out, so use a breakout board. This is a logic level converter to make it safe. Just writing data to this isn't very hard, but if you want this to be in a format that you can read on your laptop, you'll need to use a library so that you format the data in the standard format that operating systems use. Okay, the last protocol here that we're going to look at is I2C, IIC, or I2C. Again, it uses the master-slave terminology that we're trying to get away from. But this is very similar to SPI, but it adds another layer to make multiple devices talk to each other in an easy way. So the slaves have addresses rather than just a pin that you turn on and off. You send out over the data. Before you send data, you send out the address of who you want to talk to, and that way everybody's listening. They read the address coming out first, and if it's not my address, I ignore it. So we don't have to have separate wires for the address. We send that on the data. So we're agreeing a little bit more ahead of time on how we're going to send the data, how we're going to pack it. So that lets us just use 2 wires to communicate to many devices, because we send data and then receive data using the data wire, and then there's a clock wire. But there's this whole extra layer of communication, because we have to do the addressing first, and then we have to receive or transmit in the right order. So there's a library called the wire library in the Arduino that you'll probably want to use. With I2C, there are 2 lines, SDA and SCL, the data line and the clock line. And that's all you need, so it's very easy to connect multiple devices to our Arduino. In order to know if anybody's using these lines, the Arduino should check and see if they're not being used, then they'll be at 5 volts. They'll be at the high voltage for a certain amount of time. And if that's the case, then you know they're not being used. So all of these devices disconnect when they're not being used, and there's pull-up resistors that connect them to 5 volts. Which means if you don't put pull-up resistors on your I2C lines, the Arduino is just going to sit there forever thinking that somebody else is using the lines. So it's essential to put these on. Our compasses use I2C, but most of the compass boards have the pull-ups already installed. So if you look at these on an oscilloscope, we can have clock and data. So we start sending data by pulling the data line, which is pulled up to 5 volts with the pull-up resistors. We bring that down, and that means I'm using this now. So then the data pin is set when the clock is low, and the data is read when the clock is high. So you set up here, you read the data here, set up here, read the data here. And you have to do the addressing and lots of other things. So make sure you're using a library on the Arduino is the best way to go, I think. Lots of references around the web, and there's that other video if you want to see this happening live. I recommend watching that too. But that's plenty to talk about so far for serial port communication and asynchronous and synchronous serial. Remember, there are 3 kinds: asynchronous serial, or UART, SPI, and I2C are the 3 kinds that we looked at today.